So we said gamma, X-ray, UV, visible, IR, microwave, radio wave, all light. And it is strange because colloquially we think of light as the thing that it can either be bright or dim. But that's just one spectrum of frequencies that will excite the electrons in molecules in your eyes that send electrical signals back into your brains that then are interpreted. Other frequencies of light don't excite the electrons in that way. So visible light is unique to us because of the stimulation it does to our nervous system. But there are actually other types of light that stimulate your nervous system in other ways. You stood in front of a fire before, and you felt its heat on one side, and the absence of that light is cold. It's actually not just heat from the fire coming in the form of fast-moving molecules transferring kinetic energy to you and warming you up. Part of that is infrared light that is being emitted from the chemical reactions, and the infrared light is absorbed by molecules in your skin, and it's absorbed by molecules stretching their bonds, and that stretching then transfers as kinetic motion to warm you up. So you're both getting bombarded by fast-moving molecules and taking heat away from those molecules. You're also absorbing light into your molecules and getting warm from the light. You also emit infrared radiation, which is why I can see you in the dark using heat vision goggles, night vision goggles, and heat-seeking goggles is what I was trying to say. We have these security cameras at our house. Like the doorbell has a security camera in it, and at night it actually shines infrared light, and you can't see it. But it shines infrared light, and then it picks it up with its infrared camera. And it's funny because something like this, which has an obvious design and clearly different colors in the visible spectrum, shows up as one color in the IR. I might be wrong, but it's something like that. Because infrared light interacts differently with the molecules in the things that you're wearing, interacts differently with the molecules in your eye. So when we say that we're seeing something, we're just getting stimulated. I like to think when I'm listening to the radio in my car is seeing the music play. Because it's radio wave frequency that is stimulating the antenna in my car that then is being transformed into audio. So my car sees the radio wave light in a similar way that I see visible light. And the study of how light interacts with matter we call spectroscopy. Okay, I want to take you back to one of the a bridge from our last unit on chirality into this idea of spectroscopy. It's something I don't test on a lot, but it's a really interesting property of light and matter. This is polarimetry. You've actually done a little bit of polarimetry yourselves if you've ever worn polarized sunglasses. And you have worn polarized sunglasses, haven't you? Or at least you hope you have, and you didn't just get a knockoff when you paid for the polarized lens. That polarized lens, polarimetry, is saying that you're going to get just one plane of light. We call it plane polarized light. Now, plane polarized light can be a little bit hard to depict. The light that we are looking at in this room is not plane polarized. the light comes out in all sorts of planes. I want you to imagine that the light in here is just an incredible amount of angles and directions that the light is traveling in. So plane polarized light goes through some sort of filter. And on the other side of this filter, it's just one plane. Or the way the analogy that I like to use, I'm playing Frisbee, and there are a lot of different ways that I can throw the Frisbee. I can throw it vertically to my friend, I can throw it horizontally to my friend, I can throw it anywhere in between those planes. Which way do I throw it? I throw it in a plane polarized way. I throw it steady in one direction. So this is our filter. This is what your polarized sunglasses do. The knockoff polarized sunglasses, they're just tinted, and so a lot of the light is absorbed. This is not absorbing light, it's actually blocking it, and it's only allowing. That's why you still get a crystal clear image with polarized sunglasses. You're not just diffusing the light, you are filtering the light. So first, polarimetry will plane polarize the light until we get this, and then it will pass this light through a sample. Typically, this is your analyte, your molecule that you're interested in analyzing, dissolved in some sort of solvent. And as the light passes through the sample, two things can happen. It can come out exactly as it went in, at the same angle, or it can come out rotated. It can change by some amount, some angle, some number of degrees clockwise, or some number of degrees counterclockwise. Now, if you guys can remind me, I'm going to send you guys a YouTube video that I typically show in class around this. I'm going to skip over it today. Where a guy demonstrates how plane polarized light can be rotated through a sample. And the question is, why and when? When does it rotate? When does it not rotate? And what causes it to rotate? First of all, anything that does rotate it, we call optically active. An optically active compound rotates light. An optically inactive compound does not.
Are you talking about the analyte? Is
Yep.
the compound that rotates or does not rotate the light?
That's right. The analyte, whatever molecule, whatever compound we're looking at, will or will not rotate light. So I'm going to give you guys a couple of examples on compounds. And I want you to see if you can figure out what it is that changes. Here is a sugar. And a sugar is optically active. If you have a solution of sugar, it will rotate plane polarized light. Here's octane. If you have a solution of octane, it's optically inactive. It does not rotate plane polarized light. Can we name any distinctions between the two? What is similar? What's different? Chloe? One's chiral and one is achiral. Great. Anything else? I mean, one's got alcohols, one is only alkane, one has an ether, one is only alkane. So is it the chirality that does it and not the functional group? What if I gave you this compound, which remember is exactly the same as this? Do you remember the term we use to classify this? We describe it with what term? Sorry? Meso. It is achiral with chiral centers. Chiral with lots of chiral centers, achiral with no chiral centers. How do you think this will interact with plane polarized light? Will it rotate it because of its chiral centers? Or will it not rotate plane polarized light because of its lack of chirality? You think it will rotate light. So it's having chiral centers that makes it interact with light in this unique way. You think it won't rotate light. Okay, I want you to come back to this idea of rotating light. I throw a frisbee to my friend. I throw it to him in one plane. By the time it gets to him, it's vertical. Okay, assume that I've done an amazing job throwing it and I didn't put any tilt on it. So when I threw it, it was just planar. And by the time it got to him, it interacted with something that rotated its plane. Maybe it was the wind. It was definitely the air molecules in between, unless my frisbee has some sort of magnetic field that it can interact with. That's what we're talking about with this light. It's passing through these molecules, through or past or by. You guys know that radio waves pass through you without really doing anything to you. And you know they do because you have your phone in your pocket and your AirPods in your ear, and they're communicating by radio wave through your body. This is one of the reasons people didn't know if cell phones were going to give us cancer or not, because we're putting all of this radio wave radiation through our bodies. It's going through you, but it's not doing anything to you. As the light goes through the sample, it's not being absorbed by the sample. It's not changing color. It's coming out on the other side. It's just getting bumped a little bit by a little bit. Every time it interacts with the molecule, it's like it gets pulled in a certain angle. So, when you have a chiral molecule, the light is always just pulling the molecule a little bit in one direction and a little bit in one direction. With each molecule, it pulls it a little bit and a little bit more. When that molecule lacks chirality, it gets pulled one way, gets pulled the other way, or it doesn't get pulled at all. It just passes straight through. No rotation. Even for meso compounds. Optically inactive. What is the relationship between these structures? You can think about their description. Are they chiral, achiral, or meso? But I want you to name their relationship. Enantiomers? Because? Another way to say it? I think that was the same way, just in a different order. They're mirror images but can't be superimposed. Another way to identify that they're
All their
in
chiral
enantiomers.
centers have swapped.
All their chiral centers have swapped. Can I get you one? Yeah. I don't know, Andrew. They're both wedged. They look the same to me. What's the proof we have that the chiral centers have swapped? If I flip this over like a pancake so that the bond line actually agrees, then my methyl groups will line up, my carboxylic acid will line up, but the alcohols have swapped. So what we're saying right now is the chiral centers have swapped because left and right have swapped. My methyl and my carboxylic acid have changed sides. That is changing the configuration of the chiral center. Or if that's too confusing, flip this one over like a pancake so that the bond line does stay the same. Now front and back have swapped. So they are definitely mirror images, and no matter how we twist or rotate or spin or flip, there's no way that I can get them to superimpose. Non-superimposable mirror images. If I isolate one of them, it will rotate light in one direction by a certain amount, and its enantiomer will rotate light in the opposite direction a certain amount. One is clockwise, one is counterclockwise. They're equal but opposite, which makes sense because they're mirror images of each other. So as light moves through a sample of one, it keeps getting bumped in one direction. If you moved it through a sample of the other, it would get bumped in the other direction. And this creates for us an interesting possibility of a solution, a mixture. If I have enantiomers in a 50-50 mixture, light doesn't rotate at all. Because for every plus rotation, it's balanced by a minus rotation. So every time the light is rotated clockwise, it gets rotated the exact amount backwards counterclockwise. No rotation. We call this type of mixture a racemic mixture. And it's actually named for racemic acid, whose structure I don't believe I have here, but I'm struggling to remember it off the top of my head. I don't think this is racemic acid, but I think it's very similar to racemic acid's structure. In fact, racemic acid was discovered by the founder of chirality, Louis Pasteur. No one realized that molecules could have different arrangements in space until him. He noticed it, I think, on a farm. He found these crystals that had evaporated, or that had formed after water had evaporated, and these crystals had a very spiral structure to them. But crystals right next to each other, one would spiral clockwise and one would spiral counterclockwise, mirror images of each other. And then he, once this was developed, this test, they found that right-hand spiraling crystals would rotate light in one direction, and left-hand spiraling crystals would rotate light in the opposite direction. Without even knowing their structure, the bond chain, they knew that these molecules had different interactions with light, equal and opposite. So the racemic acid molecule became the epitome of a racemic mixture, a 50-50 mix. So much so that racemic now only means 50-50 mixture of enantiomers, and they renamed the compound. It's now called tartaric acid. Tartaric acid, which is related to tartar. Am I saying that wrong? Tartar. Yeah, I'm saying it too right. Feels wrong. When you have a 50-50 mixture of enantiomers, which is a long way of saying, when you have a racemic mixture, you have a racemate. A racemate is a racemic mixture. Now there's some math that we can do in here, and I'm not going to do it, but there is math. If you don't have a racemic mixture, but you have an enantiomeric excess, enantiomer A is present to a larger extent than enantiomer B, you don't get this canceling out effect, but you don't get plus X or minus X, you get some ratio of plus X because it's partially canceled out by a little bit of minus X, but not an equal amount of minus X. So if you know how much total sample you have, if you know what the right rotation can be or should be, you can figure out how much of each you have by how much it actually rotates. We're just not going to get that far in. I want to ask you guys this. Will this mixture give some rotation of light or no rotation of light? Why?
Because the first group, the second group to the first group is a diastereomer, where one of the chiral centers has flopped to the other side. And so
But add to that.
But there's a higher amount of R than S.
Maybe. What you said was they're diastereomers because one group has changed configurations, but one group has not. And that's the key point about identifying diastereomers. The two parts, dia, one configuration remains the same between the two structures, one configuration changes. That's why they're diastereomers. Also, we already know that this molecule, optically inactive. So this molecule has no impact on the light's rotation at all. Why is this optically inactive? They are, the compound is meso. The chiral centers are symmetric to each other. And we know that because of this conformation. We know it can rotate into a meso conformation, into a conformation with symmetry. And that symmetry means it's meso. So whatever rotation this gives is the rotation that we'll end up seeing. Is it a racemic mixture? No, because for one, it rotates light, and racemic mixtures have no rotation. For two, it's not a 50-50 mixture of enantiomers. Instead, we call this a diastereomeric mixture, which I think is just a very fun word. Diastereomeric. Okay, I'm going to switch it up a little bit more. I'm going to have a wedged alcohol and a dashed Br. And a molecule that is a wedged alcohol and a wedged Br. This time, both molecules are chiral. But the molecules are still diastereomers. So it's not a racemic mixture. And it's not a diastereomeric mixture that gets rotation from only one of the compounds. We know that enantiomers have equal but opposite rotations. What about diastereomers? How do you think their rotations relate? Are they connected at all?
Would it be like, for example, those hydroxy groups in the one cis bromine on the right side? Would it be an exaggeration, so it would be more the ratio of chiral spin than it would be independent?
To my knowledge, there's no relationship between the RS configuration or the combination of RS configurations with the direction that light is rotated or the extent that light is rotated. They feel totally unconnected. When all of the chiral centers are equal but opposite, you get equal but opposite interactions with light. When some of the chiral carbons are the same and some are different, you get a completely different interaction with light. So if we say that this rotates light plus or minus A degrees, this rotates light plus or minus B degrees, not related to each other. Their rotations are totally disconnected. So will this rotate light? Probably. Even if it's a 50-50 mixture, it will probably rotate light. And I have to say probably because I'll bet you could go out there and find a combination of diastereomers that just happen to cancel each other out. But their rotations are not related. So some combination of them, we don't know what effect it will have on rotation. Diastereomeric mixtures.
Those are both diastereomeric mixtures, right?
Both of these are diastereomeric. Yep. I think it's really bizarre that light can pass by a molecule, somehow interact with the molecule. I try to imagine it as this kind of swing, a pull by one part of the molecule, a push by another. And this electromagnetic force shifts its angle because it's passing by electromagnetic things. It's passing by electrons and it's passing by nuclei. And those interactions are not changing its energy. It's not being absorbed. It's transmitting straight through, but it's just shifting. I don't think I even appreciate how bizarre light is. It feels like the most mundane thing to us. Oh, it's cloudy today. There's not as much light. I like the lights in my bathroom that I can dim bright and dim low. Dim bright, does that make sense at all? But light is so weird. We can't really understand it.
So for like stereomeric mixtures,
Mm-hmm.
I don't want to say they always rotate light to some degree, but
Yeah, we could find some combination that doesn't rotate light, but your odds are, because their rotations are not related, your odds are it will rotate light.
but a stereomer of a meso compound will always rotate light. Is that?
Well, yeah, you're right. Meso compounds have no enantiomer, right? Because meso compounds are superimposable with their mirror image. But meso compounds have at least 2 diastereomers, because both chiral carbons could flip if there's only 2 chiral carbons. Okay, what is the ratio of enantiomers needed to have a racemic mixture? 50-50. Is it impossible to have a 25-75 mixture of enantiomers? No, but we wouldn't call it racemic. that just becomes enantiomeric. So this is a type of enantiomeric mixture. Racemic mixture is a subset. The diastereomeric mixture, what ratio is needed of the diastereomers to make it diastereomeric? Any ratio. Any ratio of enantiomers, enantiomeric. Any ratio of diastereomers, diastereomeric. A 50-50 mixture of enantiomers, racemic. Racemic is the most specific definition there. All right. That's one way that we can interact light with matter and glean something from it. We're going to look at 3 more techniques, and we're going to learn how we can derive chemical structure from these instrumental techniques. The first thing I want to introduce you to are your tools. I have printed out some correlation tables for you guys, but I have an updated correlation table. I just didn't have time to print all of these with what's going on with the internet. My printer wouldn't connect. So I just want you guys to pass these down for now and just take a look at the version that I had for you already. There's 2 sides because I couldn't double print it. You should have one that is front and back. And Michael, I just gave you a second pair. Did you not get 2 sheets from me?
Oh, I did. I passed it down.
Yes, you get a pair. I want you to look at the one I handed you already. I want you to compare it. I want you to compare the one that you have already to the new one that I'm passing around. Compare the table, yeah. Which again, yours is front and back. The one that I'm handing out is not front and back because I couldn't double-side it. I want you guys to compare. Actually, this would be a good group activity. Maybe you guys can form 2 groups. Compare the one that I gave all of you to the one that I gave your groups. I want you to find similarities. I want you to find differences. And I want you to report back on what you think a correlation table gives you. What is the usefulness of the tool? Let's take 5 to 10 minutes for you guys to collaborate in this. These are the things I want you to think about. What's the difference? What's the usefulness? Yeah, you guys will have to join them. I'm sorry. Pass it around. Sharing is caring. The venue had a lot of green, so we told people, like, have green accents. I wore a dark blue suit and he wore a black suit. I was like, we have no green accents. So we got our nails done for it. We picked different colors because we were very drawn to different Yeah. It's hard to get darker than this. It's lighter. It's like, it's closer to that inner green by the blue hexagon. Yeah. Yeah. It was fun. Kind of like we didn't do a bachelor party, so that was getting our nails done with our bachelor party. You guys feel like you've exhausted your comparison? What differences do you see, and can you agree on what usefulness you think these tables bring?
It doesn't tell you anything though about stereo
Mm-hmm.
mass spectrum, that looks like charge is pretty low because it's mass to charge, but the actual rotation doesn't seem. But I have no idea what almost all of that was like it's one of those things
Okay, do you feel like you've exhausted it? You want to come back and talk about it? This is not working, sadly. What differences did you guys see that you felt were worth pointing out? Can I grab those new ones back? Since you can't all have them anyways. I'll use them as my display. Thank you. Let's start with that big table. That full page table. What did you guys notice was different between the ones you have in front of you and the ones that I handed out? More lines on this one. Yeah, and different types of lines. Did you notice that? Like those separatory lines aren't all just like more bolded lines. So notice how one of them is a dark dotted line that goes right at 3,000 inverse centimeters. Do you see how the group above it ends at 3,000 inverse centimeters? The group below it begins at 3,000 inverse centimeters. I guess I didn't ask you that. Did you notice that this table was organized by range? on both of them. What, Quinn?
It was organized by something.
It was definitely organized by something.
Something there.
Yeah.
But if you look at the absorption range, you can see that it goes in descending order. That's how these are organized. And that dotted line, that first dotted line, is right at 3,000. Something absorbs until 3,000, something absorbs after 3,000. And then, did you notice that there's a matching dotted dark line at the bottom? At well, actually, it's not very clear, but it's like around that 1,300, which you guys have on your old versions. You have that dark line around 1,300, but now it's a dark dotted line that mirrors this dark dotted line up here. There's information that I'm going to draw your attention to when we get to this later in the week. And I want you to think of the same information around there. Okay, then the new one had this dark line, but it had 3 lines to it. You guys see that? And then the one underneath that was 2 lines. So the distinction here is 3 lines versus 2 lines. And I want you to notice what happens, or what's listed in the table around there. Just under 3 lines are the triple bonds. And just under 2 lines are the double bonds. What's the usefulness of this table? What does it demonstrate? A bunch of bond types. The left-hand column depicts and highlights the bond types, and then the second to the left column details that. Did you know that CH is not enough of a bond type? Because sp3CH is different from sp2CH. The difference is the orbital, the angle of the bond length, the bond strength. sp2CH on an aromatic ring is different than the sp2CH of an aldehyde. Despite having the same atoms and the same orbital, the rest of the environment also changes the bond type. The CO double bond of a carboxylic acid is different from the CO double bond of a ketone. The OH of a carboxylic acid is different than the OH of an alcohol. So the table helps us differentiate characteristics of different bonds. That's the usefulness of this table. It correlates a bond type to the way that it interacts with light. And specifically, this is infrared light. We'll talk more about it. I wanted to draw your attention to a few things. The top is all hydrogens, bonds to hydrogens, then triple bonds, then double bonds, and then at the bottom, more stuff going on. So we're going to come back and talk about IR at the end of this week. And you guys have an analysis assignment on IR for your compound, just making predictions. Some of your compounds have no IR spectrum taken, so there's no way for you to get that information. But you don't need it for your analysis. Anything else you guys wanted to point out? Differences or suspected usefulnesses of that front table? Then let's flip to the back page, which had, on yours, had only 2 tables. So that, I assume, was a difference that you guys picked up on. Different number of tables. Were any of them the same between the new one and the old one? The mass spectrum example was the same. Now the NMR correlation table, the new one has 2. And the old one didn't describe what type of NMR. The new one differentiates 2 different types of NMR. You guys see that? So on the new one, we had hydrogen NMR and carbon-13 NMR. Which one is it that you're given on your correlation table, your old one? Were you given the hydrogen NMR or the carbon NMR on your old one? Hydrogen. You notice how hydrogen is highlighted a bunch on your correlation table. So it doesn't tell you about bond type, because you'll notice there's a lot of bond types that are not listed. Instead, what it tells you is environment, regiochemistry. It tells you whether the hydrogen is in a carboxylic acid or an aldehyde, or if it's in an aromatic ring or an alkene, or if it's next to a functional group, which is about as vague as it can be, or if it's just part of an alkane. The new one added on to that and gave you a correlation for regiochemistry of carbons. So NMR is useful to us in that it helps us derive the regiochemistry. IR will tell us bond types, NMR will tell us structure. And then the last one was mass spec. And mass spec, you can see, also just gives us structure, structural fragments. And the new one has a couple of notes on it. It said, these are extremely abbreviated examples of signals you might see. One of the reasons I wanted you guys to compare and contrast is because I'm never done updating my materials. But this is a tool that I give you guys on your exams, and I want you to know that tools are never done being crafted. Could you imagine if we stopped at the first telephone and we said, that's it, I can communicate faster than ever, I'm done. If we'd stopped there, we wouldn't have Hey Siri, text whoever. Tools like this are not as useful as cell phones, maybe, but again, they're only as useful as you know how to use it. So I've got a lot of detail in these tables, a lot of nuanced information that's hidden in the way that it's designed, like the dotted line, the triple line, the double line. There's a lot of information I'm trying to draw your attention to, and I don't give you all of that information on the exam. I give a different version of the correlation table to you as a resource while you're learning, and a different version, usually a slightly more abbreviated version, on the exams. So I want you to have this tool because I think it's incredibly useful for spectroscopy, for studying how light interacts with matter in different ways. But I also want you to not need this tool with all of the little helps that it gives. I want you to develop the strength on your own as well. So take a look at the practice midterm. Look at the practice final, and you can see the abbreviated forms that I give you. Usually it's just not drawing out the structure or not giving some of the wording. And you'll see exactly what it is when you look at the practice midterm and the practice final. Use these resources. Learn how this tool can help you grasp these concepts. All right, here's another fun fact. This is material in our textbook that gets covered in chapter 14. Does it feel like we're at chapter 14 already in the semester? We started with chapter 1 a few weeks ago, and we're already at chapter 14. We skipped a lot. Now, our textbook for OChem 1, I'm supposed to teach you chapters 1 through 11 and 14. So I'm skipping 12 and 13 because that's how we start OChem 2. And I had the bright idea a few years ago, if I'm skipping 12 and 13, why can't I skip 5 through 13? Right? If 12 and 13 come before 14 by necessity because I need to teach 12 and 13 before I get to 14, I shouldn't be skipping over them, but I am. So I can skip over as many as I want to get to what I want to. And you know that we've been learning the fundamentals of organic chemistry right now. The nitty-gritties. My bonds rotate around and I can get different conformations. Despite that, my molecules have absolute configurations in space no matter how they rotate. And these are the functional groups when they are in the molecule in this connectivity. We've just been hashing out so many details that just help us understand organic chemistry. And that's what we're going to do one more time with this unit. Spectroscopy is really just a tool to help you understand organic chemistry a lot better. After the midterm, we're just doing reactions, which is like not the fun conceptual stuff. And I truly believe that this unit will help you understand reactions way better having this down already than if you learn it after we learn all of our reactions. I've taught you a lot about molecules already. I think somewhere in there a thought might be formulating, a question might be formulating, how in the world do we know that these structures exist? How did we figure out that this is how they're bonded? This is how they're arranged. This is how they're connected. And that's what spectroscopy does for us. We leverage instruments to get data, often about how light interacts with matter. And from that data, we can back calculate what bonds are in our structures, where the hydrogens are placed, where the carbons are placed, how they're bonded to each other, what molecular fragments do I have in my structure, and we can piece together a molecular structure. That's our goal with spectroscopy. Okay, this worksheet is going to be a little dim in certain parts, so I will help you guys fill in some of the structures that got faded out. No, I had a busy weekend and didn't come in until 7 this morning.
That's right.
Sorry.
No, that's okay.
This will be on Canvas after class, especially if you remind me, and maybe if you don't. Oh, and Michael brought up a good point. None of the correlation tables talk to you about stereochemistry. None of them help you differentiate between R and S chiral carbons or plus and minus chiral molecules. That's what polarimetry did for us. But like I said, there's no relationship between clockwise rotation and R or S carbons. So really, polarimetry just tells us chiral molecule or even chiral mixture. It doesn't give us any more information beyond that. Any of you guys ever crawled into a nuclear magnetic resonance instrument? Did you say maybe? Like that's the skepticism. That's the skepticism you should have in a class like this. I don't know. Maybe I have. You guys ever crawled into an MRI? Okay, then you have been the analyte in an NMR experiment. You were the sample being analyzed, but we call MRIs magnetic resonance imagery instead of nuclear magnetic resonance imagery because no one wants to crawl into a tight little box that makes a really loud noise that starts with the word nuclear. People just aren't interested in that. But when you're having an MRI done, they are analyzing the nuclei in your molecules. And the chemical environment changes the environment of that nuclei and changes how its signal goes off. So the setup. We have an instrument that is just a big magnet. And I mean, it's a powerful magnet. It's so powerful, it generates a lot of heat that it's cooled down by a layer of liquid helium. You guys know helium, right? Second element on the periodic table, which means very small. Does not bond. Does not have very strong intermolecular forces. Terrible, terrible van der Waals forces because of how small it is. So to be a liquid, this needs to be in the single digits Kelvin. This is less than 10 degrees Kelvin. Liquid helium wrapping this magnet, and then wrapping the liquid helium is liquid nitrogen, just as a second shield. And this is all held inside of airtight, vacuum, zero pressure separated chambers to try and mitigate any heat loss, trying to keep this magnet super cold. Inside the magnet is a sample tube or a probe. And the magnetic field spins around this probe subjects your entire sample to a magnetic field, and then it has antennas, receivers inside of it all too. And what it looks for is radio wave frequency. These receivers pick up radio waves. Now I'm gonna keep this one kind of small. Do you know what? Actually, I'm gonna start with this molecule called TMS. Oops. Yes. Always hard to remember whether T is tri or tetra. We use TMS during NMR experiments as an internal reference, a standard, because very few other molecules, especially other molecules of interest, interact in NMR the way that TMS does. TMS is a standalone molecule, so it makes for a really good reference. When this is under the magnetic field, all of the nuclei inside of the atom are subjected to the magnetic field. But we can fine-tune what we are looking for, what we're receiving. So we're going to start by talking just about proton NMR. Under the magnetic field, all of these different nuclei have different nuclear spins. Okay, so you guys remember that electrons have spin. And the options for electron spin, +1/2 or -1/2. Spin up, spin down. Electrons are pretty nice that way. Nuclei are a lot more complicated. It depends on the number of protons in the nuclei, in the nucleus. Depends on the number of neutrons in the nucleus. It depends on the mass of the nucleus, so the combination of protons and neutrons. Nuclear spin can be +2/3. It can be minus entire integers or plus whole integers. Nuclear spin is just crazy. Nuclear spin can also be 0. We're going to pay attention just to hydrogen, and specifically the H1 nucleus, proton, no neutron, which is different than the nuclear spin when there's deuterium, H2, proton, and neutron. So we're studying H1, which is not the same as H2, which is often just referred to as deuterium. We're going to be studying this. Under the magnetic field, all of those nuclear spins become aligned. And they become aligned with the magnetic field. It takes some energy to align all of those nuclear spins. That's what the magnetic field is doing. It's essentially pumping energy into the nuclei, and then the magnetic field turns off. And those nuclei, which have just been brought to this high energy state, they start to precess, they spin around, and then they relax by emitting radio wave frequency. We excite the nuclei, and then we watch for their relaxation. That's the setup. The spectrum has relative intensity on the y-axis. So we're not looking at specifics on the y-axis. We're not going to pay attention to a unit on the y-axis. We would, if anything, we would say arbitrary units here. We're just not paying attention to that at all. On the y-axis, on the x-axis, we label chemical shift. And the chemical shift can be abbreviated, or the unit can be written as ppm or as delta. We will use both. You will see both things to abbreviate the x-axis.
Is that parts per million?
It is parts per million. Yes. And we think of parts per million typically as concentration. Oh, the concentration of carbon dioxide in the air is reaching some level of ppb or ppm. But I want you to think of this actually more as frequency. How often does something occur per 1 million occurrences? That's all concentration is, actually. Concentration is frequency. How frequently will I interact with something once I interact with 1 million parts of it? Now, if we're looking at the proton NMR, our range is typically from 12 ppm to 0 ppm. When we look at carbon NMR, the range is typically much, much bigger. Carbon NMR goes from 220 to about 10 ppm. Do you notice which isotope of carbon we analyze? We're analyzing carbon-13. Carbon-12 has one of those combinations of protons and neutrons in its nucleus to make it NMR inactive. Carbon-12 doesn't align with the magnetic field because it has no nuclear spin. Carbon-13 has an odd mass in the nucleus, does have has a nuclear spin, does align with the magnetic field, does give off energy. I'm so upset by how crooked that line is. Yeah. Wow. You can't tell from the side. But notice how different the range is. That's just a side effect of the nucleus itself. Carbon-13 is a much bigger nucleus, so as it relaxes, it gives off a lot more energy, a higher frequency signal. We get these signals, or we get our spectrum, and then we get signals in them. So I just want to point out at the top, I give you that signal tetramethylsilane, TMS. And it has a signal right at 0. That's actually the point. That's the point of TMS. We put TMS into a sample, and then we tell the software, we tell the instrument, make that signal 0 parts per million. That's our baseline. Then look at phenoxynyl, which I don't know if yours looks as bad as the one in front of me. There's a lot of bonds missing. Phenoxynyl has all sorts of signals. There's a signal around 1, kind of looks like a temple. There's a signal around 1.6. There's a signal around 2.2. There's a signal around 4.5, 4.6. There's signals between 6 and 8. There's a lot of signals in there. And then look at ethyl acetate. Much fewer signals and much clearer shapes as well. There's obviously one signal around 1 that has 3 distinct peaks. Signal around 2 that has 1 peak. And this is something we're going to talk about. We're going to talk about how the signal is one unit that has individual peaks. Questions so far about NMR, the setup, and the spectrum? We have an NMR right behind Jackson, but through the wall, on the other side of the wall. Oh, no, actually on the other room. Okay, never mind, further away than I thought. We have an NMR, and NMRs are fairly expensive instruments. They can, depending on the type you get, they can be really challenging to maintain. The one that we bought last summer was bought intentionally for student use. So you guys in lab will get to run NMR samples. The second half of the semester, you'll be analyzing the products of your reactions by NMR. If you were to take OChem, especially OChem Lab at any other institution, CU Boulder, Stevens Point, the University of Utah, you would never run an NMR. You'd take your sample and you'd give it to a TA and they would run it for you. But at Slick, you guys will actually have an experiment where you get to just familiarize yourself with running it before you use it to characterize your product the rest of the semester. Very fun. And you're basically just giving your molecules a little MRI. And the way that the chemical shift tells you what type of environment your hydrogen is in is what your MRIs are doing too. It says, well, look, all of these nuclei look the same. It must be a fatty area. All of these nuclei look the same. It must be a muscular area. All of these nuclei look the same because those hydrogens then show up in specific types of molecules. All right. So first, let's talk about equivalent sets of hydrogens. I distinctly remember learning this when I was in OChem 1. My professor drew a molecule on the board and said, how many unique hydrogens are there? And I said, what a silly question. It's all hydrogen. What's unique about it? But it's true. They're all hydrogens. What's different about them? What's different is what type of environment they're in. Consider TMS, tetramethylsilane, with the compound that I gave you in that second row on the far left, neopentane. They have the same number of hydrogens. Would you agree? They all have 12 hydrogens. Yeah. Are all 12 of those hydrogens identical or unique from each other? Neither? Then what would you say? There's 4 groups of 3?
Can some of them be identical and some be unique?
Sure. Which ones would you say, let's just look at TMS. Which ones would you say are identical to each other? Which ones would you say are unique from the rest?
Say they're all
A hydrogen bonded to a carbon, bonded to silicon. That regiochemistry description, remember how we used that, we leveraged regiochemistry when we were deciding whether 2 groups were distinct in chirality? And we said a chiral carbon bonded to a primary carbon, bonded to a tertiary carbon, those must be different groups. A hydrogen bonded to a carbon, bonded to silicon, all the way around. All identical. Meaning they'll all give off one signal. And when you look at the NMR spectrum for TMS on the top left, there's one signal in the spectrum. What about neopentane? How many signals would you expect to see? How many sets of hydrogens would you expect to see? Just one set. All 12 are identical. They're connected differently than TMS, but notice it's a hydrogen bonded to a primary carbon, bonded to a quaternary carbon. All the way around, all 12 hydrogens can all be described the same. But would you say that these 12 hydrogens are the same as TMS's 12 hydrogens? No, because one, the hydrogens are bonded to a quaternary carbon. The other, the hydrogens are, or the groups are bonded to a silicon. And look at those 2 spectrum. TMS shows its signal at 0. Neopentane shows its signal 1 ppm. So they are different signals, but they produce the same number of sets of hydrogens. All right, the next structure, 1,3,5 tetramethylbenzene, has a lot of symmetry. It's got symmetry right down the middle. It's got symmetry diagonally up. It's got symmetry diagonally down. What that symmetry tells me is that the 2 hydrogens on the aromatic ring at the top are identical to each other because they're symmetric to each other. And the 2 hydrogens, the 2 methyl groups here are identical to each other because they're symmetric to each other. And with all of that symmetry, all of the methyl groups are symmetric. All of the aromatic hydrogens are symmetric. This gives me 2 sets of hydrogens, which means that I should expect 2 signals. And how many do we see in that NMR spectrum? 2 signals. One just past 2, and one just before 7.
Does the height matter?
We're going to talk about the height later. But remember, height would just be relative intensity.
So
And we'll talk about that in a little bit.
So is that like the amount?
Nope. We're going to come back to it. So by looking at a molecule, I should be able to predict how many signals should I see. Well, let's look back up at the middle top one, phenoxynyl. I know you can't really see, but how many sets of hydrogens do you think there are? Those 2 methyl groups at the top right. They reflect into each other. They're symmetric. So 2 methyl groups gives 1 signal. Then there's a tertiary carbon they're connected to that has a hydrogen. Then there's a different methyl group on the bottom right. Then there's the hydrogen bonded to the amide. Then there's another CH to the left of the amide and another methyl over there as well. And then there's 3 different aromatic hydrogens. I'm thinking we should see 8 different signals for phenoxynyl. 8 unique sets of hydrogens, 8 different signals. And when you look at the spectrum, 1, 2, 3, 4, 5, 6, 7, not bad. But 7's not 8. So how is it I'm expecting 8 signals, but I'm only seeing 7? Some signals overlap with each other. And despite the fact that they are expected to give different signals, it doesn't mean that their signals can be differentiated from each other. Some signals overlap, and that's something that we will hit on. Usually appear separate, sometimes overlap. All right, then there's the chemical shift. We can look at a molecule and predict how many sets of hydrogen there are. Predict how many signals we expect to see, but what about where those signals show up? We already noted that TMS gives a signal at 0 parts per billion, but neopentane gave a signal at 1 part per billion, despite being very similar. 4 methyl groups bonded to a central tetrahedral atom. The distinction between silicon and carbon separated these signals. Just that little distinction changes it. Chemical shift. Changes in chemical environment shift the signal. Look at your proton NMR correlation table.
And that signal is the radio wave that's been given off.
The frequency of the radio wave.
Frequency of the radio wave.
Yep. The nature of the radio wave then transforms into the chemical shift signal that we see. So different chemical environments change how the nucleus interacts with the magnetic field, changes the frequency of the radio wave that it emits as it relaxes.
So how does parts per million equate to the radio wave?
Yeah. Well, first of all, we set TMS as a reference. So we say whatever signal TMS is giving off, that's 0 parts per million, or you might think of that as no different from the signal of TMS. And then for every change in frequency relative to TMS, we can correspond it as some part per million. There is heavy math involved. Fourier transforms that take the actual sine waves that have constructive and destructive interferences. Like if one signal gives off this sine wave, but another signal gives off this sine wave, then what the instrument actually sees is something like this.
Okay.
combinations of sine waves just give one final wave, but the Fourier transform deconstructs what the radio antenna sees into its constituent parts, and then takes these frequencies and plots them out in the parts per million domain.
What is it, parts per million of?
I mean, think of it as changes to TMS's signal. It's not a concentration.
Okay.
It's a frequency.
That's weird.
It is weird.
Like the chance.
The relative change in frequency, the change in frequency relative to TMS's signal. So changes in chemical environment. Here's some general trends that you guys can see. Less electronegative groups. Appear to the right. More electronegative groups appear to the left. Hey, maybe I shouldn't say this because I'm just looking at hydrogen. Hydrogen doesn't change from more electronegative to less electronegative. What I mean is the chemical environment. A less electronegative chemical environment shifts more to the right. A more electronegative chemical environment shifts more to the left.
And that's the same as the periodic table.
Well, no, electronegativity trends up and to the right. So no relationship to the periodic table. So look at your correlation table. What would be the least electronegative chemical environment that a hydrogen could find itself in? Alkane. Because carbon isn't working to steal electron density. Well, actually, silicon is less electronegative than carbon. So by replacing that central tetrahedral with silicon or carbon, less electronegative shifts more to the right. Okay, it is weird to some people that 0 is on the right-hand side. So do with that as you will. More electronegative, carbon is more electronegative than silicon. Notice how when you get out of the alkane group and you get adjacent to functional groups, it shifts more to the left. The weird thing is that it's not just electronegativity. That's a good trend, but it's not just electronegativity, because then alkenes have their own region. Aromatic rings shift even further left, but then being adjacent to the aldehyde, being adjacent to the carboxylic acid, very electronegative regions. And what we're actually referring to here is shielding and de-shielding. Shielding from what? From the magnetic field of the instrument. Electronegative groups steal electrons. Well, you guys know that electrons interact with magnetic fields. So if the electrons stayed around the nucleus, the electrons can shield the nucleus from the magnetic field. But if the electrons are getting stripped away from the nucleus is going to interact even more strongly with the magnetic field. Interacting more strongly with the magnetic field shifts to a larger frequency signal, shifts the signal further to the left. The last thing I'm going to leave you with today, a bit of an oddity. ROH hydrogens, alcohol hydrogens, and NH hydrogens, amines, they actually don't shift as far left as you'd think. I mean, I can't get much closer to an electronegative atom than being bonded to the oxygen or the nitrogen. You'll also notice that these aren't on your correlation table. It's like the two types of H's not on the correlation table. But because of hydrogen bonding, these get de-shielded from electronegativity, but then they get re-shielded because another atom hydrogen bonds to them and gives them electron density back, shielding them again. So these have a range from 0.5 to 5 ppm. A lot tighter than you'd expect. a lot further to the right than you'd expect. It kind of breaks our rule. You guys are okay with that? Quinn said no, but everyone else is all right. We're going to talk about integration and splitting patterns tomorrow. We'll do some practice, and then we're going to dive into infrared spectroscopy. Yeah?
With the alien sense of hydrogen, can you explain again how we can find the other two signals? Because in this example, you drew 3 lines, right? There's only 2 sets, not 3.
Sure. So you guys are welcome to go. Thank you for your time. I'll explain this one if you want to stick around. This molecule has 3, 6, 9 hydrogens attached to methyls and 3 hydrogens attached to the ring. Why does it not give 1, 2, 3 different signals for the methyl groups? Why doesn't it give 3 different signals for the hydrogens? But these hydrogens are symmetric to each other, so they give the same signal. And then because I can show that plane of symmetry in all those directions, they're actually all symmetric to each other.
So you have like 2 sets of equivalent or hydrogens.
2 unique sets of hydrogens. The methyl groups are all the same. That's 1 set of hydrogens. We agreed that all of the hydrogens in a methyl group are the same.
Right.
And here we're saying all of these methyl groups are also the same. But then you look at phenoxynyl at the top, and a lot of them are distinct from each other.